This is Andrew, and this is Keen On, the daily now.tv chat show with some of the world's leading thinkers and writers. Hello, everybody. It is Wednesday, August the 23rd, 2023. A couple of very interesting headlines today. One from The Verge about how one day brain implants might be able to restore communications with people with paralysis. New York Times reports on something similar, the way in which AI is able to restore someone's ability to speak, to somehow replicate their brain. All very inspiring and optimistic. In our age where people are somewhat fearful, even sometimes apocalyptic about AI, artificial intelligence, which I guess in a broad sense is a way of trying to create artificial minds, artificial brains. One man who's given a great deal of thought, a lifetime's thought, to neuroscience in the brain is my guest today. Rafael Yuste is a professor of neuroscience at Columbia University, one of America's leading universities, and he has a new book out. It's just out, Lectures in Neuroscience. And he's joining us from his home in the Upper West Side of New York. Raphael, welcome. Congratulations on the book. Should we view some of these pieces with a pinch of salt? The idea that brain implants could one day restore communications for people with paralysis, it seems almost magical.
Thank you, Andrew. Thank you for having me here. It's not magical. It's not science fiction. It's science. It's medicine. This is happening, and this is one of the reasons that I'm bullish about neurotechnology, is so that we can end up helping these patients with brain diseases. It's not just paralysis. I mean, if you think about it, everyone in the show has personal experience with friends or family that suffer from some sort of brain disease, either Alzheimer's, Parkinson's, epilepsy, mental handicap, paralysis, stroke, you name it. No? And we know perfectly well as medics that there's very little we can do for this patient because we need the technology to get into the brain to be able to decode what's happening and to change it in order to alter the prognosis of these patients. So it's not at all hype. This is science, and this is the way that science is evolving right now.
It's almost a truism today, Raphael, that people say that the human brain is the most intricate and complicated object in the known universe. I remember having someone on the show and said that, and I have to admit, somewhat skeptical, and I'm anything but an expert in this area. Is there any truth to that?
Well, I mean, it's a little exaggerated, but it is an absolutely fascinating piece of matter of an enormous complexity. I mean, think of it, your brain has about 86 billion neurons, and each of the neurons is connected to probably about another 100,000 neurons. So you do the numbers, the connectivity of the brain is equivalent to 3 times the entire internet of the earth. This is each of our brains, okay? Just imagine that you're walking around with 3 internets inside your head. No? So we know very little about how the brain works. We know a lot about what the molecular and cellular components of the brain, but we haven't really put that jigsaw puzzle together yet. No? But the one thing that we do know, and it was already known by the Egyptians, okay, is that the brain is the site of all the mental and cognitive abilities of humans. So this is essentially what defines us as a species, our thoughts, our memories, our emotions, our imaginations, our behavior. All of that doesn't come out of thin air, but it's actually generated by those 3 internets that we have inside our head, no? Inside our skull.
Yeah, it's a very interesting way of putting it, Raphael. We are walking around with 3 internets in our skull. You talk about each of us having around 86 billion neurons. What is a neuron?
So a neuron is a cell that has a particular characteristic. It's electrically excitable. In fact, it looks a little bit like a transistor. It can either be on and off with an electrical signal of about 100 millivolts. And this, again, every one of these 80,000 neurons is connected to, let's say, another 100,000 neurons. We don't really know the exact number, and receives connection from another 100,000 neurons. So it's a little unit in a gigantic network. And the biggest challenge in neuroscience, and one of the biggest challenges in mysteries in biology, I would say, is how the joint activity of these networks of neurons, how somehow they magically generate our minds.
So we don't know how those neurons actually connect. We know we've got all these neurons, but if you like, the operating system is still a mystery.
That's right. We figure out, I mean, neuroscientists have been at it for 100 years, generation after generation, in a network that stretches through space and time. We're part of the same team, and some of the brightest minds of every generation have gone into trying to figure out how the brain works. And we know a lot about how the neurons are actually physically touching each other and how they tickle each other and they fire each other. But what we're missing is what we call the neural circuit level. And imagine you have a computer, you open up a computer, and you find that it's built out of transistors. Well, that's great, but that doesn't help you understand what the computer does, because you have to figure out how these transistors are connected, and in their connections, they build circuits that implement particular mathematical functions, and using those functions, your software can actually operate. So we're in neuroscience, we're at the level in which we know the transistors, so to speak. We are starting to figure out the connections, but we're still not there. We're missing what is the circuit level, and we're missing, of course, the algorithms and the software that so to speak.
So would it be fair to say that at this point in August of 2023, we're relatively ignorant about how the brain operates?
We're ignorant, but there's light at the end of the tunnel.
We know we're in a tunnel, Raphael. There's no doubt about that.
We're totally in a tunnel. We've been in a tunnel for 2,000 years. But in the last 20 years, through the application of new neurotechnologies, of new methods to measure the activity of many neurons at once, and to be able to turn on and off neurons selectively, we're starting to see, some of us are starting to join a hypothesis that could explain how you go from the activity of individual neurons to the human mind. How do you go from neural activity to thought?
How did you get into this? As I said, you're a professor at Columbia University, one of the great universities in America. Did you stumble into this? Have you always had a calling? Where were you born?
I'm Spanish. I'm from Madrid, from the center of the town. I was turned into a fledgling scientist by my mother when I was 14. She gave me as a birthday present a book called Microbe Hunters from the Cruyff. It's a beautiful history of the glorious years of bacteriology, where people like Pasteur and Koch and Spallanzani figure out that infectious diseases were created by bacteria. And that was, to me, like a calling to my heart, because it painted this romantic idea in my mind of these scientists that are working in the basements of their institutes, huddled over their microscopes, isolated from the world, anonymous many times, and they're discovering the secrets that help humanity. No? And I decided that's what I want to do when I grow up. I wanted to be one of those scientists that is looking at the microscope in the basement and figuring out the secrets of life. And then neuroscience was a very logical choice. Being a Spaniard, the most important scientist in the history of Spain is Santiago Ramón y Cajal, who's the father or the grandfather of neuroscience. He worked about 100 years ago, and he was the one mostly responsible for the idea that the brain is built out of individual neurons. This is what we call the neuron doctrine, that the single neuron is the unit of structure and function of the brain. So everywhere you go in Spain, there are streets named after Cajal, schools named after him. And he was a wonderful writer. He wrote these spectacular books, very candid about himself, about his problems. And so I became a Cajalian. And I was always also very interested in philosophy. In high school, that was my favorite topic. I used to read in the waiting for the bus, The Critic of the Pure Reason by Kant. And so all these things merged together in a career studying the brain as a scientist with a microscope to try to understand how the brain generates the mind. So I think all of these things have been threaded together in my life. I've been lucky, I've been privileged, I've been able to go in this direction, and I had wonderful mentors, particularly one mentor in Cambridge, in England, Sidney Brenner, who was also a medic like myself. I was trained in medicine, and he took me under his wing in his lab. And he essentially yanked me out of medicine and threw me into research. And he also shipped me to the US. He said, go west, young man. And I never looked back.
It's interesting talking about Cambridge. Old friend of mine, Martin Rees, I'm sure you're familiar with his work, the Astronomer General. He's been on the show, and I've talked to him many, many times over the years about the awesome nature of looking into space. I'm guessing that the experience of looking at all these neural networks is a similarly awesome, perhaps even spiritual experience, isn't it?
It's not just spiritual, it's also aesthetic. These neurons are absolutely beautiful. I'm in awe at the beauty of nature. In fact, if I had to argue what drives my career is the pursuit of beauty. As scientists, you don't normally think of scientists as in the same category as artists, but I think we're made out of the same stuff. No? You take a painter, and the painter works in a studio, which is normally all messy and with all kinds of paints and half finished pieces of work all over the place. And he or she expresses his or her ideas in an imagination, a creative process, and puts them onto a canvas. No? So scientists, we're just the same. No? We work in laboratories, which if you walk into my laboratory, like, oh my God, I cannot believe how disorganized this is. There are all kinds of computer circuits, electrodes, molecular reagents all over the place. No? And that's our canvases are the setups with which we do our experiments, and we paint using our creativity and our imagination, the ideas that we're trying to test, and we contrast them with nature. And if nature says check, then we go and publish them into our work, which are research papers, which I take pride of crafting them as beautiful objects, just like an artist would craft a beautiful painting. So we write beautiful papers. We try to make beautiful arguments, tell a story, illustrate it beautifully, and that's what we pass to the rest of the world.
And this aesthetics you talk about, the beauty of the brain, it's the aesthetics of systems, isn't it? The way in which all these things fit together. Maybe we don't understand it. I assume, in a way, Rafael, it puts us, even though we've got these brains, in our place, doesn't it?
Well, there's two things to your question. First of all, the aesthetic process of creating beauty, which I would argue in science is just resembles the same as in the arts. It's the same process. We just create with different media. No? There is a moment in the life of a scientist when you finally understand something. It's like when you put together the jigsaw puzzle, like, oh my God, click. That's the last piece. Everything fits. And that moment, it's unforgettable. That's also what drives us. I had a few of those moments in my life, and I go to the lab every morning at 7 a.m, anxious because of the possibility of understanding something that no one understands. And this reminds me of the particular day in which I decided to switch from medicine into science when I was in Sidney Brenner's lab. And they told me the story of how Sidney, Francis Crick, and Leslie Barnett performed the experiment that discovered that the genetic code had 3 letters. And this was a super elegant, one of the most beautiful experiments I've ever heard of my life. No, it was like playing chess against nature. And they did the final move, and it was checkmate. So they figured out the genetic code had 3 letters. And Crick famously told Leslie, do you realize that we're the only people in the world that know that the genetic code has 3 letters? So this idea, this is what gets me out of bed every morning. We're playing chess against nature. We're trying to figure out how the brain works, and we're getting close to the end game. And one of these days, we're going to say, checkmate. This is the way the brain works. And then that day, I could turn around and say, we're the only people in the world that know how the brain works.
Yeah, Rafael, that should be the title of your next. Probably someone already has it as a title: Playing Chess Against Nature. It's a fascinating conversation, and I'm gonna come to Columbia, and I think I'm gonna major in neuroscience, Rafael, because you put it in language that makes sense even to non-scientists like myself. We're talking with Rafael Yuste, a professor of neuroscience at Columbia University, one of the world's leading neuroscientists. He has a new book out, Lectures in Neuroscience, which presents all this stuff in very accessible, coherent way. I want to take a short break, thank our sponsor of this show, Liberties, a quarterly journal of culture and politics that puts culture and politics in an accessible way for ordinary readers. We're going to run a short ad for that, and then we'll be back with Rafael Yuste, the author of Lectures in Neuroscience, to talk a bit more specifically about the book itself. So don't go away, everyone. This is a fascinating conversation.
Beyond the news, the noise, there is nuance, insight. Liberties is not just a journal of ideas. It's a meteor of intelligent substance. It's the place to be for engaged citizens. Politics, opinion, substance. Liberties is a triumph for freedom of thought. A quarterly of urgency, of cultural exploration, of intellectual delight, of immaculate prose. It's invaluable. Subscribe now or find Liberties at your favorite bookseller.
And you can subscribe to Liberties and find out more at libertiesjournal.com. We are talking with the great neuroscientist at Columbia University, Rafael Yuste, who has a new book out. It's out this month, Lectures in Neuroscience. It's accessible, Rafael, but you are offering your own particular theory. At least that's my understanding. You suggest that the conventional idea of the brain is that it's an input-output machine that reacts reflectively to sensory stimuli, but you argue something else. Is that fair?
Yes, that's totally fair. That's the whole point of the book. No? I was telling you earlier that we still don't understand how the brain works. We've been at it now for over 100 years. And the current model of how the brain works, the one that's in every single textbook in neuroscience, in the first chapter, is that the brain is made out of neurons, thanks to Cajal, and that these neurons are connected in particular ways, and that the brain is a machine that reacts to sensory stimulus and through some sort of bucket brigade generates a behavior, a motor output, okay? And this idea was actually coined and burned into the soul of neuroscience by one of Cajal's contemporaries, Charles Sherrington, who was also in Cambridge, and he argued that the brain is a table of reflexes. He actually studied the knee-jerk reflex, and he figured out how that works. As you know, in the knee-jerk reflex, if you tap your knee, then you can get a little stretching of your leg, no? And he figured out the neuronal mechanisms of how that happens. And said, oh, this is easy. The brain is old. It's like a gigantic phone book of reflexes. No? When you see something in the outside, something starts to move inside, and boom, and you perform a behavior. No? You see the ball coming towards you when you're playing football, and then you process that information and you kick your leg to hit the ball. The problem is that this model, although it's very appealing and simple, has really not brought home the bacon. We've been at it for 100 years and we still don't understand how the brain works. In fact, we still don't even understand what happens to the brain when it breaks down, the mental or neurological diseases. So it's funny enough that in the same lab as Sherrington, there was a young student, Graham Brown was his last name, and he was quite a rebel. And he started to roll the ball of the possibility that the brain is not just an input-output machine, it's something different. It has its own agenda. It has an internal rhythm, an internal activity that is the whole purpose of the brain, is to generate this internal activity. And when you get an outside stimulus, sometimes you react to it with a behavior, sometimes you don't. And vice versa. You may have a behavior without having an outside stimulus. So you focus from input-output, you focus the light on the inside, on the intrinsic activity. And these new technologies that have been developed in the last 20 years, and I've been a very strong proponent and part of it, of this group of people that have developed these methods to record the activity of groups of neurons in the brain, is demonstrating over and over again that Graham Brown was right, that the brain is all about this intrinsic activity pattern. And if this is the case, then we can finally build an intellectual bridge that connects the activity of the neurons with a thought. And if we cannot do that, then we can try to start to explain the human mind in biological terms. And this would be...
In a sense, does this suggest that the brain is almost a universe itself, or that there's no real separation between the individual brain and the world?
Well, so we're not the first ones to argue that. In fact, it was Immanuel Kant, whom I read
I was thinking that.
Yeah, so he fired the first shot. Well, you could argue the first shot was fired by Plato, no? But Kant definitely got it right smack into the bullseye, no? Because he said, wait a minute, the reason why our mind agrees with the world could be because our mind reflects the world, which is what the British empiricists had argued, like Hume and Locke and Berkeley. Or, he said, what if it's the opposite? If the world reflects our mind, if what we think is out there, in reality, it's all in here. And this is exactly the point of the book, to try to tell that story from the point of view of science with modern discoveries and with hardcore data. The ship is pointing directly into Kant's direction. I would argue that what we perceive as reality is internally generated.
It's a remarkably fascinating observation or argument. Throwing another big scientific thinker in here, Darwin, does this suggest that there was some natural process? I mean, the brain hasn't always been as it is. Is that fair, Raphael? That it's never standing still, and as Darwin suggested, its evolution reflects what, a form of survival, an attempt to conquer the world around us or integrate the world?
I would argue the brain is evolution at its best. Nature invented the first nervous systems about 750 million years ago, at the end of the Diacaran. And these are the cnidarians, whose modern relatives are jellyfishes, corals, sea anemone, and hydrozoans. And it turns out that, according to this point of view that I'm defending in the book, the whole reason why evolution invents the nervous system is to be able to predict the future, okay? Because if you're a species that you can predict the future, you have a leg up in evolution, survival of the fittest. Well, guess what? You're more intelligent. You're going to see what's coming. You'll be able to survive. You'll be able to avoid being eaten or eat in this prey-predator competition. You'll be able to find the right mate and reproduce more than the poor guy next to you who cannot predict the future. No? And it turns out that to predict the future, according to this theory, what the brain is doing is generating a virtual reality model of the world. And it's running that model backwards and forwards in other words, to try to see which direction the world around us is going. Now, because nature has 750 million years to sculpt out that model and to sharpen it up, it's such a good model that as humans, we confuse the model with the reality. That's how good it is. And only sometimes when we're asleep, when we're having hallucinations, or when daydreaming, there's a disconnection between what's in our head and the real world. But most of the time, it's really accurate. In fact, it's very difficult to find under the rug the places where the two things don't match. And that's those. I illustrate a lot of those examples in the book, because that's where you can point out in this chess game with nature, you can say, checkmate, I know what you're up to. I figure out what you're trying to do here.
Yeah, so in a way, Rafael, what you're arguing, or if your argument's correct, AI itself is a piece of all this. There's nothing unnatural about AI. In a way, the attempt to predict the future and create this virtual reality of the world, that's what AI is. So AI is a literal extension of the brain. Is that absurd or fair?
I don't know. I mean, I would stick to what I know best.
Well, you know about all this AI work. I'm sure you've read about it. You may not be an AI expert, but are they? That's right. In a sense, borrowing your narrative to apply to technology?
I don't know, and I don't care. Whatever, anyone can borrow whatever they want. Now,
no, and I don't mean that critically. I mean it's almost, but it makes a lot of sense, and it brings a much more human element to AI, because if what you're saying is right, it makes AI very human.
Well, I interpret AI as algorithms to solve optimization problems, which is essentially problems where you're choosing for an optimal solution within a whole variety of different possibilities. No? And so people use the term artificial intelligence, but to me, it's actually a metaphor of a metaphor. First of all, we don't even know what is natural intelligence. So the word intelligent for me is a metaphor for a bunch of higher cognitive abilities that humans and other animals have. No? So when you talk about artificial intelligence, you assume that you know what is the natural intelligence and that you're sort of replicating it in a computer. I don't know. I mean, I wouldn't go that far. I think the AI, which I completely admire and use it in our research and in our lives. No, it's an incredible useful tool, but I would take this to be just another tool that humans have built in our long history. I mean, we're tool builders. If I can quote another philosopher of Martin Heidegger, who defines humans, this is the species that builds tools. So this is just another tool. It's and
I guess I'm trying to say that it's a brain tool. You mentioned dreams. How do dreams fit into this narrative? Were you suggesting that a dream is the brain functioning at half pace or in a different way, in a surreal way without the world?
Andrew, we know so little about the brain that we still don't know what the hell is a dream and what the hell are they good for. So that tells you how ignorant we are as neuroscientists. It's embarrassing that we cannot explain what our brain is doing 1/3 of our time on Earth. We're sleeping and we're dreaming. I cannot tell you that it's clear what exactly is a dream, what is the function of a dream.
Right, and Freud, of course, famously argued that the dreams reflect our reality. Is that still conceivable?
I don't know. I think, I mean, I would label this as an opinion rather than a scientific theory of Freud, with all my respects to his work. No, which of course he didn't have access to the data that we have today. No, but there's something critical about sleeping and dreaming. You know, if you deprive an animal of sleep and a human of sleep, you end up killing the animal or the person. And if you reduce the dreams, you have major impacts on cognitive abilities of human, on memory. So it's linked to, probably, I'm just speculating here, but for this machine to keep itself running smoothly, this brain machine, this endogenous activity that Graham Brown dreamt of, no? The dreams are something fundamental. They may be doing the cleaning up of the metabolites, or fixing up the broken wires, something that is really absolutely
so it's
critical.
fixing itself. That's a fascinating way of putting it. Rafael, you know as well as I do, you live in New York. We live at a time of great pessimism. Everyone fears that humans have screwed up on every front: political, cultural, above all else, environmental, in terms of other species. We've done lots of shows with naturalists of one kind or another, environmentalists, who suggest that humans have much to learn from other species, from the birds, from the bees, from other mammals. My understanding is that no other species, no other form of life have brains which compete in any way with what we have as humans. Is that fair? And should we be a little bit more, should we be prouder of our brains, of our place in the universe, this remarkable system, this 86 billion neurons that we still don't really understand?
Well, first of all, I think I'm definitely more on the positive side of the history of humanity and the moment that we live in. I think what we do live is in a moment of great exaggeration, great hype, and great tremendism, as they say in Spanish. No? For whatever reason, I don't want to get into the sociology of that. No, but if I look back as a scientist, and as a medic, the progression of humanity in the last 100 years has been spectacular. I mean, even in my own life, when I went to medical school, over half of the cancers were deadly. Now you can cure 90% of cancers. So of course, I'm not saying that we don't have major problems ahead, but I'm a firm believer in the ability of science and medicine, which is the application of science to health, to help humanity. No? And in principle, there's no problem big enough that we cannot all work together, particularly the scientists, and solve it. No? So with respect to the other species, again, as a scientist, as a medic, I can tell you that we're just like any other mammal. We have we have our brains. The chassis that we have is the same chassis that other mammals have. In the laboratory, we study mice. Mice are mammals, and they share a lot of the same brain that we have. We just have a larger brain. And we should be proud of our large brain, because it could be the pinnacle of evolution in terms of this ability to predict the future. If that's what the brain is doing, and I would argue that, I'm arguing that in the book, if you compare ourselves with other animals, we can see deeper into the future than any other animal. Imagine you take a fly, no? So maybe the fly is worried about what's going to happen the next 5 seconds of its life. You take a little slug, or maybe they're worried about the next day. Or take a mouse, maybe the mouse is worried about the next few days. But you take a human, and we're worried about what's going to happen to the human species for thousands of years. So we have this virtual reality model of the world that is also extremely precise. No, we do have probably the most dense neural network in terms of brain circuitry of any other species. If you take together not just the number of neurons, but the number of connections, For our body size, we're just way out of proportion. In fact, one sign of this is the fact that our heads are gigantic, and nature cannot make our heads bigger because we wouldn't be able to be born through the birth canals of women. So, and that's why, I don't know if you know this, when a baby is born, you can actually, it's incredible to watch that. As it gets pushed through the birth canal, as soon the blades of the skull are overlapping on top of each other. And as soon as it's out, they finally pop up, and then the head becomes larger, and then he cannot go back in. That's it. So that tells you that evolution is increasing the size of our brain, particularly the size of our cerebral cortex, as much as possible. Because in this evolutionary game, the survival of the fittest, we definitely have a leg up here, having this great processor to compute the future.
You talk about the survival of the fittest. You talked about Immanuel Kant as well, who, of course, was the great moralist. What's your theory of how the brain generates morality? Are these bound up with one another? Are some of these billions of neurons, are they creating our sense of good and evil, or does that come from somewhere else?
It comes from there because there's nothing else. It's not like we have another organ in the body that generates morality. No, it comes from the brain. That's where it's at. But we don't understand how. I don't know how it comes, morality is generated. And I would argue that it's not just humans. I just argued a second ago that we're just another mammal. I'm sure that the moral thought and responsibility and compassion is shared with other species. No? And why we have that? So that's a fascinating question. Maybe there's an evolutionary advantage to having more morality for the survival, not of the individual, for the survival of the species. No? Maybe that's the reason. No? I think that was an argument made by Stephen Jay Gould, no? That there is some elements of species-driven rules that get embedded in the societies of humans. No?
Well, finally, fascinating conversation, Raphael. For me, at least, as someone who doesn't understand neuroscience, and I know your book is designed for that audience, Lectures in Neuroscience. You mentioned that we are playing chess against nature, but we've only just started. We're nowhere near the end of the game, although there is light at the end of the tunnel. What happens when that game ends? Will we be able to fix conditions like Alzheimer's? What would be the result of understanding this system that you say, for the most part, we're still fairly ignorant about?
Two outcomes. The first one is to understand scientifically who we are. What is the human mind? What defines a human being? What is the scientific mechanisms and reasons that generates our thoughts, our morality, our emotions, our love, our memories, everything that we are. And that, I think, is going to be a new renaissance. If you look at the history of humanity, the Renaissance, we come out of the Middle Ages, and suddenly we figure out that we're not the center of the universe. We're just another species in this big planet. No? And that had a tremendous positive impact in society, in politics, in science, in art, in medicine. It was a revolution. That's why they call it the Renaissance. So we think we're approaching the Renaissance 2.0, where we're going to finally understand who the hell we are. We've been at it for thousands of years. This is the heart of philosophy. What is a human being? What is the human mind? Imagine understanding that. And then the second reason, which is even more important, has to do, as you mentioned, with the patients. The reason that we urgently need to understand how the brain works is because, as a medic, if you want to deal with a disease, if you want to cure a disease, you have to understand what we call the pathophysiology, which is a complicated word, but it's actually very simple. The pathophysiology is when the function of an organ, the physiology of the organ, goes pathological. Okay. In order to understand the pathophysiology, you first have to understand the physiology, the function of the organ. So you go to the heart disease. Well, guess what? We understand the function of the heart, the physiology. We understand the pathophysiology of, let's say, a heart attack, and we can go and help the patient and save some of them. No? But with brain diseases, guess what? We don't understand the physiology, let alone the pathophysiology. So, but with this new understanding of how the brain works, we'll be able to put the foundations. So it's like a building, so that the next level up, the clinicians will jump in and say, oh my God, now I have the physiology. Let's go for the pathophysiology of every one of these brain diseases. What is schizophrenia? What happens in Alzheimer? What happened in epilepsy? One by one. And just like if you go back in history and look at the continuous progress of medicine, step by step, we'll get there. I'm sure we'll get there. So I think that's the future that I work for, that I strive for, and that I've devoted my whole life to.